Hi everyone, welcome to my session. My name is Krizhanovsky. I'm CEO of Tempest Technologies. And to introduce why this talk, let me first talk about what we actually do. We develop high-performance software. The first one is Tempest FW. It's a fast hybrid of HP accelerator and firewall. In this project, we developed very fast, or maybe the fastest HP parser, fast or fastest HP TLS handshakes. We also use a bunch of lock-free data structures for web cache, for message bus. So we target security and performance with Tempest FW. Also, we have our client project, typically network security and data storage systems. That could be custom machine learning classification for web application firewall or high performance regular expressions for DDoS mitigation, or it could be S3 or NFS servers. And at the moment, our client demands us to build the fastest S3 and NFS servers. Besides the whole project, from time to time, our clients ask us to optimize existing software. And typically, the most performance comes from algorithms and mathematics, but it also a lot about careful programming and getting the maximum from your compiler and hardware. Typically, we use C and C++, and sometimes we use assembly. During our work, we do code reviews, and one of the examples could be, for example, in code you can see function with three operations, and we know that there is a Hacker Device book which proposes two operations for the same functionality. So we might be wondering whether it makes sense to write more complex code or compiler is smart enough to do the optimization. In this particular case, the modern compilers are smart enough to apply the hacker's delight trick and to generate exactly the same code. However, another example isn't so straightforward. In this case, we allocate array either using plain C or on the stack, or we use GCC built-in alloc function. To have a look on the code, I will use Compile Explorer. It's a very helpful tool to explore the resulting assembly code for different platforms and compilers. So in this case, I compiled the code with GCC on the highest optimization level, and we see that GCC generates different code for both the cases, and apparently the second one isn't so efficient as first one. If we compile the same code with Clang, then let's so we see that the code is exactly the same. So the answer depends on the compiler, even for such simple examples. Next, let's talk about x86-64 platform. During this talk, I'll be focusing on this platform. The architecture is superscalar prefetching, and with superscalar, we mean that any given time, most likely several instructions are executed by CPU. The instructions are executed out of order, but they're retiring, in other words, their results committed to memory and registers in order. Instructions consist of several micro-operations, and instructions has different latency. Latency means how many CPU cycles the instruction takes in dependency chain. And different throughput. Throughput means how many instructions of the same type can be executed in parallel. And typically, we work with reciprocal throughput. So as higher value we have, the lower throughput it is. To explore the architecture, let's use LLVM MCA tool. To do so, I will compile the code, some code by GCC for my architecture. I will ask compiler to generate assembly code, and I will pipeline the output of the compilation to LLVM MCA. I also ask it to analyze code for my architecture, to build timeline graphs, and provide bottleneck analysis. Let's explore the output. So my architecture has dispatch width 6, and in average there are 4.6 instructions executed in parallel, so which is very close to 6. So the parameter isn't bad. Reciprocal throughput is about 10. It's also not so bad. Next, the tool shows dependency and the resource pressure. We see that resource pressure isn't so high, dependency is much higher, but still not so high, as we'll see further. Also, the tool provides you good analytics about the dependency. In this case, we see that dependency is crucial for us. So in this particular example, we see that instruction 12 depends on instruction 4, and we see hints from the tool what the dependency is on. So using the tool, you can work on your assembly code, reorganize it, and improve throughput. Next, this annotation about the micro operations and latency for the used instructions. On the very left column, we have a number of micro operations per instructions, and we see that most of the instructions have only one micro operations, except several ones, right? Next is latency, and we see enormous large latency for end branch instruction. Also, please pay attention to vector instructions, which have much higher latency than basic instructions. And this reciprocal throughput, which shows how many instructions can be run in parallel. So, like we can say that these two instructions are going to be run in parallel. Next, I want to show you timeline view, but in this particular case, everything is synchronized with end branch instruction. So let's review timeline in another program. In this case, I compiled the program. It's a different program this time, but I compiled with control flow protection disabled. And let's have a look what we have for this program. This program has much lower number of instructions per cycle, much higher reciprocal throughput, so we see that performance measurements is much worse for this case, and we see that data dependency is 90% in this case. This is much more work to do in this program. Thanks to disabling control flow, we don't have end branch instruction, and now we can see out of order execution in action in more convenient way. With out of order execution, we see, for example, that two instructions are dispatched at the same time. However, the second one is going to be executed while the first one is waiting for execution. The second one finishes execution before the first one, but they both retire at the same time. So we see that different instructions start in different times, they execute in different time, but they all retire in order. So this out of order execution and in order retirement. Let's back to our slides. So what end branch instruction is? Essentially, this protection against return or call or jump-oriented programming, and what it actually means. Suppose we have two functions. Authentication function with FN, which is responsible for user authentication, and authenticated with FN, which does some logic after user authentication. And both the function, at least the first one, is carried from the virtual table. And we do this using RIX value. And if attacker can change the value of the register, they can jump to authenticated with a friend, so they can elude authentication. To prevent this attack, compiler generates end branch instruction for authentication function, and when CPU executes call instruction, it starts internal final state machine. And if the call lands on end branch instruction, then everything goes fine. However, if the call lands on any different instruction, we have exception. So there's no execution of non-authenticated users. Actually, that's not the only CPU mitigation of attacks. Another attack example is Spectre, and let's have a look what it is. In this code sample, we call do something if set of the array is smaller than array length. This is pretty normal code. However, array length might be somewhere in the memory, so CPU has plenty of time for out-of-order execution. And if CPU branch predictor predicts that do something is a likely branch, it starts to execute do something. If at some point array length is available and we decide that this branch is wrong and we need to go on a different branch, then all results from do something are discarded by CPU. However, do something could affect CPU cache, and the cache state will remain after rolling back of the changes. To prevent the attack, the attack itself in that attacker can observe the CPU cache, for example, from concurrent thread running on hyperthread on the same CPU. So this is a side channel attack. So to prevent this attack, we should compile the source code with mRedPaline option. In this place, compiler just adds epilogue, which is normally non-reachable. And if we decide that do something is a wrong branch and we need to go to a different branch, we also prefetch this epilogue, and we execute pause and barrier instruction, which actually clears the cache state. Another maybe not so recent attack was Meltdown, which allowed an attacker from user space to reveal data in the kernel space. To mitigate the attack, we had to use different page tables for kernel code and user space, so we have much more expensive system calls, and they could cause severe performance degradation up to 30%. And thanks to running in the Linux kernel in tempest.fw, we do not pay for this mitigation. Next, let's back to our compiler optimizations. So if we analyze the source code and try to figure out which code can be optimized, we can read the compiler documents. However, it's not the most efficient way, and the compilers provide command line options which do show in which places, which lines compiler do optimizations, which kind of optimizations, and in which places optimization is possible but could not be applied due to some reasons. Of course, if you have some more hard case or you need to get the maximum from your code, you should analyze assembly code and probably use tools like LLVM and CA. Let's consider one of practical examples, and in this case, this will be HTTP parser. And in case of tempest.fw, we have a huge state machine. Typically, HTTP parser is a loop over input data, and there are nested switch statements. The one switch statement over the state for state machine, and another is for input data for each of the states. So during this code, you jump to different states, you remember the current state, and you can continue the loop. So basically, in the body of the loop, you drew a lot of jumps. In Tempest, we have magnitude larger state machine rather than in Nginx. The reason for this is that Tempest applies a lot of security checks to stop web attacks on HTTP level. And basically, even a small HTTP parser state machine is comparable in size with first level of instruction CPU cache. To optimize switch statements, compiler provide several optimization. One of them is lookup table. So if your states are integers with consequent values, for example, 0, 1, 2, 3, and so on, then compiler just generates lookup table and uses the lookup table as offset for, like in this case, register RX to jump to the right label. And in this case, we see that this is exactly the case for Spectre attack or jump-oriented programming. So if we need to protect our code against Spectre or jump-oriented programming, we need to compile the code with mred polyne. And in this case, compiler fails to binary search algorithm to find the next label to go. And also the same technique is used if your states are non-sequential integers like 0, 100, 200, 300, and so on. Actually, during the compile time, compiler knows all the labels. And by the way, modern compilers are smart enough to optimize if-else chains, just like switch statements. Compilers know all the switch labels, and basically they could generate perfect hash, just like a lookup table for sequential labels, but in this case we can generate perfect hash for non-sequential labels. There was a proposals back 15 years ago to provide perfect hashing for switch optimization, but it wasn't implemented neither in GCC nor in Clang versions. To deal with the problem, we applied the same approach as Weigel. So all the case statements were paired with direct labels, and instead of spinning in a loop and adjusting the internal state, we just directly jump to the right label. So we use just goto. The drawback of this approach is that we have to consume our input data also with each of our jump. However, the drawback isn't so big because if you have a pretty large loop body, then compiler basically does the same. For example, if you have a loop statement, for example, for statement with conditions, and you have a very long loop body, then compiler puts the loop conditions several times inside the loop body. This is optimization techniques. So we basically do very similar as compiler normally does. The next thing is that with the previous technique we optimized the most of the loop iteration. However, we still have to have case and switch statements for the first entrance into the loop. And we can get rid of if all the switch and case statements if we use the compiler statements to which allows us to use label addresses and store them in local variables. In this case, we store the address of labels in parser state, and we can use the variable to make a direct jumps to required state machine. So essentially, we have a large state machine of direct jumps. If we benchmark this approach with simple switch statement, we found that for large state machines, for example, for 400 states, we can go 2 times faster. However, for smaller state machines, basic switch statement is much more efficient. I mean the very small, like 7 states. The reason for this is that we have a lot of branch misses. So for large state machines, it's more crucial, and additional code introduced into the loop is negligible. Um, Interesting thing about this is that while go-to-driven automaton is still about 2 times larger than switch-driven, it experiences 2 times smaller number of instruction cache misses. So the state machine is larger, but instruction cache is used more efficiently. The next thing about state machine is that with HTTP semantic, we always have firstly HTTP header, and next we have a bunch of HTTP. Sorry, first we have HTTP method, and also after that we have bunch of HTTP headers. So HTTP state machine always first see HTTP method, and after that any HTTP headers. However, compiler doesn't know this and can rearrange the code in any arbitrary way. So we found that processing get and post requests, the most frequent methods and actually the first states which state machine faces come to the end of the function. And at the beginning of the function, the compiler moves some unlikely methods, HTTP headers. So the first thing which we tried to cope with the problem was to use compiler barrier to split, for example, HTTP methods from HTTP headers. However, the barriers work not absolutely, but about relative codependency. So it processes code for get and post independently from each other. So if get has some code which is reachable only for get but not reachable for post, compiler is free to move the code closer to get and move post under the code. So essentially, compiler still arranges the code around the barrier, but surely it don't move the code which depends on get on above of get. What actually helped us is to use likely, unlikely, and hot and cold compiler hints. We also tried to use profiler guided optimization, but we face the same issue. Profile-guided optimization relies on CPU time spent in particular pieces of code. For example, some HTTP headers could take a lot of time to process. For example, there could be cookie, which can be several kilobytes in size. From the other side, HTTP methods is very quick to parse. So profile-guided optimization will move expensive cookie processing on the top of state machine. However, we still first parse HTTP method and only that HTTP cookie. With compiler hints like likely and hot, we still can point out that the code under likely branch or under hot label is goes first. The code under unlikely branch or under code label goes the last, and non-specified labels and branches are somewhere in the middle. So with this tool, we managed to get optimal code layout for our state machine. We also played with different compiler optimization options, and we found that all three can generate even slower code than all two. To understand what's going on, we tried to compile the code without the optimization options available on third level, but not on second one. And we found that some of the options are really helpful and improve the code performance, but some of them make the code less efficient. If we use only the most beneficial options in our case, then we can get the fastest code and faster even than on optimization level 2. Um, some of the bad optimization options are about after vectorization. After vectorization uses single instruction multiple data, and this when many uh, may, the same operations on many data can be executed in one instruction. So, for example, if you have an array of 32 bytes, it can be added with another similar array with only one instruction. However, the instruction, as we saw in MCA output, have higher latency, and also they require additional alignment, and actually not all the code are after vectorizable. Having these drawbacks, compiler employ very sophisticated heuristics on when they actually need to apply after vectorization. And I reference here a pretty good talk from LLVM developers meeting. Linux kernel also uses single instruction multiple data, but only for subsystems which really benefit from it. And one of such subsystems is cryptography. The reason for that, kernel doesn't use after vectorization. And the reason for this is that vector instructions are executed on FPU, which has separate state from regular CPU registers. So when you switch between user space and kernel space, you need to explicitly store FPU state, and this is very slow. So if we benchmark simple copying with FPU store and restore, we see that it can be 10 or 20 times slower. In Tempest FW, we do use single instruction multiple data, but we do optimization minimizing FPU context switches. What is after vectorization? There are documents about what the compilers, both Clang and GCC can do for after vectorization, but basically there are about two types of code. The first one is loop vectorization, when several loop iterations could be executed as a single instruction multiple data instruction. And another one is when we have a sequence of operations, similar operations on different data, we can pack the sequence in a basic block and execute it on vector instructions. Also, compilers allows you to specify different cost model. It's how beneficial vectorization is. What's the relative cost of using virtual vector instructions? Uh, what's the requirements, code requirements to be after vectorized? First of all, not all instructions are vectorized. Only operations which are supported by vector instruction of the CPU is applicable for this. There should be no data dependency. We'll have a look on for this on an example. And it's better to use countable loops, but even uncountable or infinite loops are still optimizable by modern compilers. Let's have a look on some examples. I will start from C++ example. This example is from this blog post. There are much more examples about C++ STL, and I compiled it with optimization options allowing AVX2. And we see that compile exposure further highlights in gray the assembly lines corresponding to std accumulate, and we see that 32-byte registers are used in this case. Let's do more um, investigations. In this case, we have a look on a code which is typical for cryptography. There's a bunch of very similar operations run on different data. And by the way, this replicate computation. Let's have a look how compiler compiles it. I used compiler options to show optimizations, and we see that no any optimizations were applied. In this case, I explicitly stated that cost model is unlimited. It means that we should apply any vector instruction, they are cheap. And now compiler says that it made optimization on line 54. This line we see a very small block of code in comparison with the rest of the code, which was actually optimized. This code works with independent data, and we see, for example, from the code above that there's data dependency. And this is why compiler even didn't try to optimize the code. Let's have a look on another example. In this case, this loop optimization vectorized. In previous example, it was basic block optimizations. In this case, we have another cryptography routine for 16 iterations. So let's have a look how it is optimized. GCC did some optimizations on line 20. Let's have a look for Clang. Clang didn't do any optimizations. However, in Clang, we can ask the compiler to make vectorization for the loop, to force it with pragma. And in this case, Clang shows us error that it cannot optimize the code. That was a bug report in LLVM several years ago, exactly about this case. And compiler author stated that if loop changes the memory and it reads the memory, then this loop cannot be vectorized. However, GCC was successful in this vectorization. We played with after vectorization for our HTTP parser and cryptography routines. But for HTTP parser, we have very small basic blocks. We don't have any vectorizable loops. So the extra cost for vectorization doesn't make sense. Additional latency and additional requirements for alignment, because kernel has a different alignment from user space using after vectorization. Elliptic curves are actually a good place for after vectorization, and this is why I shown both the examples for elliptic curve cryptography. But the thing is that all the cryptography stuff is actually written in assembly. In our implementation, an OpenCell, VoiceCell, and any other high-performance cryptography implementation. So let's have a look why. Basically, public key cryptography deals with very large integers, like 256 bits, which is essentially 4 8-byte unsigned longs. If we do the computation, we deal with limbs. In this case, a limb is the maximum size of normal data like unsigned long. And if we consider to add one 128-bit integer to another 128-bit integer, we can write C code like on the above. So we add the first operand to the second, and we must care about carry bit for the second addition. However, modern architectures provide us specialized instructions. So we use a specific instruction which cares about carry bit. In this case, we have not only more efficient code because we don't involve branching, but also more readable and simpler code. The last thing which I wanted to cover is concurrency. Recently, we saw a multi-threading um, application which used spin lock in their code in user space. All the application threads had affinity per CPU affinity. So basically, everything looked good. However, we found that some of the threads was waiting for on a spin lock. So essentially, the thread did buzz loop, and operating system schedule treats such processes or threads as batch processes and reduces their time slice. However, processes like monitoring require CPU time only from time to time and basically for short periods of time. So operating system schedule treats such processes in better way and provides them more CPU time slice. And we found that the kernel thread, which was already waiting on a spin lock, was evicted by monitoring thread, less crucial process, which was running on the same CPU. And that causes significant tail latency for up to 100 milliseconds. Another problem with user um, space spin locks is that the thread holding spin lock can be scheduled, and time waiting on a spin lock will be just enormous for another thread. So if you use spin locks in user space, you should care not only about CPU affinity for the working threads, but also place the CPUs, designate the CPUs only for this application, and do not allow other applications like monitoring, even if they seem just not so CPU hungry to run on the same CPU. PerfScat timehist helped us to review the problem, and the perf shows CPU histogram about what's going on schedule level. Also, x86-64 uses strong memory model or total store ordering. This C++ example from C++ concurrency in action, and it uses memory barrier. It makes sense to use memory barrier because we have similar operations, the same read operations or write operations, and we do care about ordering. However, thanks to TSO, compiler generates code without any barriers. And moreover, there was a talk on CPPCon 2019, and in that talk, the authors use different strategies for lock-free algorithms, which actually relies on x86-64 TSO. And interesting enough is that they use a Texart instruction to cope with unwanted preemption. That's all from my side. I'll be happy for your answers, for your questions. And so thank you for listening. Bye bye.